Okay, thank you very much, and thank you very much for inviting me to this nice conference. Actually, and sorry, I changed the title because I realized that well, maybe 2/3 of the people here have never encountered with this kind of subject. So I decided to start from the basics. Okay. And sorry, another 1/3 of the people, you might see the same slide several times, but anyway. And so, my talk is based on these two actually papers, and both contains more than 100 pages. So, I have to, talk this in 30 minutes, so that I should cheat sometimes, okay? And so what we were doing is a kind of analysis on fractals, and that means so analysis on fractals, and what we have done is the construction of mainly the diffusion process on these type of self-similar set, okay? And then we analyze the asymptotic behavior of heat kernel. Oh, sorry. Asymptotic behavior of heat kernels, or the spectrum of let's see. It's very strange. Okay, so and then the diffusion process is associated with the Discrete forms, and which is considered as a W12 Sobolev space. Okay, so in general, on Euclidean spaces, for example, the 1P Sobolev space is defined in this way. Okay, so f is a function in LP, and this is gradient, or the nabla f, and nabla f to the p, the integral is finite. That's as a Sobolev, 1P Sobolev space. Okay, and so how can we extend this to metric spaces? And one of the early idea is that use the Lipschitz functions. Okay, for Lipschitz functions, we have a counterpart of this nabla u. Namely, if u is a Lipschitz function like this, then you will think about the difference in the ball and divided by r, and take supremum and take rim sup here. Then it's a kind of local, Lipschitz constant, and use this one instead of this one. Then you can find something. You can define something. That's one way of defining the Sobolev space on metric spaces. And actually, there are well-developed theory on this idea. So this first one is Hiwash, and then Chiga, and then Negas, who gave a talk on Monday. Okay, but we found, actually I don't found, those two people, Casino and Murugan, who will be the next to the next speaker of this session, they found that this Lipschitz construction never works for the Sierpinski carpet or other fractals, other self-similar sets. So we need something different for those sets. Okay? And what can we do? And my naive idea, actually this is the essential idea for, okay, let's think about the interval and divide the interval into half and half and half, and think about this discrete energy. Okay? And okay, then if f is smooth, or even if f is in W1P space, so you can easily show that with this scaling constant, and taking a limit as n tends to the infinity, you will get this, the P energy. Okay. So how? And I don't care about, so this is a way, you can define the P energy without the nabla F, okay? And what my idea is, basic idea is, okay, let's think about the general, compact metric space, XD, and okay, let's find some finite graphs which, approximate this, original metric space, okay? And for this finite graphs, you can define the, discrete version of P energy like this, okay? And now the problem is, are there any good scaling constant here? And under this constant, so as n tends to the infinity, this value goes to some nice limit, and the function, this function is rich enough, okay? That's the basic idea what I am going to do. And actually, this is the graph approximation for the case of the Sierpinski carpet, okay? So, let's see. And the point is, we will not care about the counterpart of nabla F. Okay. And there are two problems. So when does this strategy work? Okay. This is the first problem. And this is, what I will do is, so try to find the criterion for general metric spaces when this strategy works. And that my answer is the notion of so-called conductive homogeneity, okay? And the other question is, so what are the explicit examples? Are there new examples other than Sierpinski carpet or, the Euclidean space? And actually, originally, I want to talk about this part, and my example today is a so-called locally symmetric regular Jacob-based self-similar set. This is too long, but you will see what it is in a time. And actually, my ultimate goal, or my dream, is reconstruction of analysis, not starting from derivation, okay? And well, if somebody says something like this, I would think he's crazy. And I think I'm crazy, okay? Okay, so let's proceed. Oh, and this is the fine. Okay, so before we proceed, the idea like this, discrete approximation and then take a limit, was for the case of P equal 2, actually this idea was used to construct, the Dirichlet form on Sierpinski carpets by Kusoka and To, okay? This was 1992, okay? So almost more than 30 years ago, okay? And since at that time we can, from the probabilistic point of view, Barlow and Bass constructed, the Brownian motion on Sierpinski carpet from the scaling limit of Brownian motion, okay? And actually, since then, until recently, we don't have any new examples, okay? So we just know Sierpinski, we have just Sierpinski carpets. And, and now new example which I obtained is like this. This is a self-similar set with very exotic shape. The most notable feature is there is no symmetry, global symmetry. Okay. And this is another one. This is actually this has no symmetry actually. And actually, Kao and Q has constructed the diffusion process on completely different. Sorry, are there any? Okay, so completely different, example, but So, and this is what I suppose to talk, So this regular polygon-based locally symmetric self-similar set, and unfortunately, I don't have time to give you a definition or anything, but you can look at this. So this is a triangle-based. So first triangle is here, and I will divide this by the smaller triangles, which fit together very neatly. Okay, and this is a pentagon-based one. Okay, this one. Okay, and in this case, actually, so there is a contraction mappings and whose contraction ratios are the same. I would denote this contraction rate as R here. And here is another example. This is the hexagon-based one, okay? And this is octagon-based one. And actually, what I can show you is that for those sets, those self-similar sets, my theory works. And I have a kind of Sobolev space. In particular, P equals 2, I have a nice diffusion process. Okay. So what's the general idea? First, to proceed with my strategy, first I should set up the discrete graph approximation of the space. Okay. And the idea is so-called the partition of a metric space. And that is, in harmonic analysis, it is known as the dyadic cubes. And the rough idea is, okay, I have some, wall space here. And then next level, I will divide this wall space into several pieces. Okay. And next level, I will divide this one into 3, and this one into 2, this one into 3, okay, and so forth, so on. And so here is some notation that first one is T0, and it starts from phi. This is kind of root of our tree. And next level, I have T1, these 3 pieces. And next level, I have these, and each piece has its ancestor actually, And S1 is a kind of children of this one. And I will try to find this kind of partition of the space. And this is for self-similar set, you can easily find a nice partition. Because, for the case of Sierpinski carpet, you have 8 contraction mappings, and you can, put the number 1, 2, 3, 4, 5, 6, 7, 8 here. And next level, you will divide each piece again to the 9 pieces. Okay, so for self-similar set with n contractions, the natural partition is, Tm, and this is the mth level, okay, which is I1 to the Im, and each I1 to the Im belongs to the 1 to n, okay? And SW is the children of W, is just add, W1, W2, W3, and Wn, okay? Like here, we have a 1, and then the children is this one, okay? So, and then when I establish my partition of the space, I mean the graph approximation of space, what I will do next is I will construct the edges. And in this case, I will do the simplest way. And what is the simplest way is I will make an edge like this one if these two pieces has an intersection, okay? And so this is the first level graph. The dotted lines are the vertices, and this is the second level, okay? So in this way, now I have the graph which approximates the original, metric space. And so the notion of conductive homogeneity, yeah. And I assume that the partition of the space is good. Sorry about that. So what is the notion of good is I don't speak here. But believe me that, those good conditions are satisfied for my example, namely the regular polygon-based locally symmetric self-similar set, okay? And of course, for the Sierpinski carpet or square or, those, familiar sets. Okay, so now we have a graph here, and I denote rho n. This rho n is graph distance. Okay, graph distance means that if you have, the graph distance between this and this is the minimum step from here to here. So in this case, graph distance between these 2 points, 2 vertices are 1, 2. Okay. And also this one, gamma MW, is actually a ball with radius W. Okay. And I assume there exists a good measure, mu. And in the case of, the self-similar set, it's just, Hausdorff measure. And in the case of PLS, the Hausdorff dimension is log n over log r. R is the contraction ratio, n is the number of the contractions, okay? And here is some, shape of the neighborhood. This is W, and these are the one neighborhood, and this is B, and this is the two neighborhoods, okay? And then I start to think about the discrete energy. And let's see that, so A is some subset of the Tn. This is nth level of vertices. And define a P energy on A by this, sum. So that, Fw, the difference between the values to the power P, and those, those edges are included in A. Okay. And then what I will define next is, 10 minutes left, I suppose. Yeah. So P conductance between A1 and A2. Okay, what I will do is that, let's pick up A1 and A2. The A1 and A2, this is A, and A1 and A2 is, disjoint subsets, okay? And I will define the conductance, P conductance between A1 and A2 at mth level. So what I will do is that, let's fix the value of the function 1 here and 0 here. Okay? And then define these cells further mth level. Okay? So define it to the next m generation. Okay? And think about the energy, P energy of the function f here. And think about the infimum of those functions. Okay? And in the case of actually P equals 2, this is conductance, real conductance between these two sets at the mth level, mth generation, okay? And so why I'm doing this is what I want to do is I want to find out the scaling constant of the energy. And actually, this should give you the scaling constant because, if you change m, then you will, I would expect that, this behaves like some power of some exponent. And that exponent should be the exponent for the proper scalings, okay? And in particular, so let's fix W, okay? And fix the, the neighborhood. This is, in this case, this is one neighborhood. And think about the conductance between the outside of this one neighborhood and the W, okay, at the mth level. And that is this notion, okay? And, okay, so there are many, of course, vertices, and take the supremum of this value, this conductance, all over the space, all over the world. And what I will know is, I can prove that there is actually this limit, okay? So we can extract the exponent, always. And surprisingly, so this exponent has close relation with some geometric, dimension of the space, which is called the R-force regular conformal dimension. And what it is? So, if you change the metric of the space, metric space, then you can change the dimension, okay? And the problem is, how much can you lower the dimension? So it is easy to, increase the dimension because you can just take a power of the original metric. And in this case, what we will think is, okay, let's change the metric, which is quasi-symmetric to the original D. And quasi-symmetry means that, finite bounded distortion of balls, okay, like the quasi-conformal mappings. And also I will put the condition where, and there should be the alpha R-force regular with respect to measure, with respect to rho, okay? And then this alpha is the Hausdorff dimension under this new metric. And think about the infimum of such, metric as measures. You change the metric measures and take the infimum. That's the R-force regular conformal dimension, actually. And what we know is that originally this was a result by Carrasco-Piaggio, and actually, Bruce Kleiner told me that he has similar result before him, but, and originally they had a result on, here, this part is not E, but they use the modulus of curve family, but I changed here to the, the energy, the conductances. And the result is Rp is less than 1, if and only if P is greater than the R-force regular conformal dimension. Okay, so this analytic notion and this geometric notion has a strong connection here. And so here I should give you a definition of conductive homogeneity, but today I don't think I have enough time. And just believe me, there is a nice notion of conductive homogeneity, and I just present you the equivalent condition here. And first of all, if XD satisfies the P conductive homogeneity, then this one behave very nicely. Okay, 5 minutes. Yes. Yeah, actually, there is a what? Okay, so this, EMPW and RP to the minus M, this is in the bounded region. And please note that, C1 and C2 is independent of W. Okay, so the space is very homogeneous, actually. And this theorem says, this theorem says, for P larger than the R4 regular conformal dimension, that means Rp, our scaling constant, is less than 1. Then, then our P conductive homogeneity is equivalent to this condition. And this looks like very complicated, but the spirit is, okay, let's choose any W tilde and any W. And in this side, we will think about the conductance between W and the complement of some neighborhood, okay? And this is this value. And here, we will fix the value K and think about any two UB from, case descendant of W, and think about the M, conductance, M generation conductance between U and B. Then it is always comparable, no matter where W tilde and W, no matter where U and B, okay? It only depends on the level of K. So this means that, the space is quite very homogeneous with respect to this notion of conductances, okay? And then, we have a nice, we can construct a nice, well, I would say counterpart of Sobolev space. And actually, the consequence of the conductive homogeneity is that, for case P is larger than R4 regular conformal dimension, then, so we will take, okay, let's think about the function f in LP. And PMF is a kind of, integral average to make the function, to discretize the function. And then think about this scaled version of the P energy. And in this case, take the supremum on take 1 over P. And this is NPF, sorry. And what we know is, okay, define WP. This is a function space, where the WP is the function which has NPF is finite, okay? Then we see that this NP is a nice semi-norm, and with the original LP, norm. So this space is a reflective Brownian Banach space. And this WP is nicely embedded in the continuous functions. And each function in this space enjoys this type of, Helder continuous estimate, okay? And the hope is now we can define the P energy, and then we have to try to extract the P Laplacian or, P harmonic functions or, anything more than that. But my study is just in this stage. And Naotaka will talk about something more. And okay, 1 minute, I suppose. And in particular, in the case P equals 2, actually, like the case of, these figures, okay? So we have a nice diffusion process with nice heat kernel estimate. And so the question is, so what happens for P is less than R4 regular conformal dimension? In this case also we have a nice Banach space, but we don't know it is regular or not. And the open problems are if P is in this regime, so what happens here? And actually this problem was solved by Murugan and Simiz for the case of Sierpinski carpets. And another problem was, okay, I finished at this line. So WP is embedded in the continuous function if and only if P is larger than the R4 regular conformal dimension. You remember that for the ordinary Sobolev embedding theorem, this part is the dimension n of the space, Euclidean space. And in case of the metric measure space, the dimension n is replaced by this dimension. And this was actually solved by these people. Okay, thank you very much.
Questions for Jun?
Hi, Jun. When you're doing your decomposition, the dyadic, I can't remember. Did you mention anything about the diameter of the pieces? Does that matter, or?
Oh yeah, that matters. Yes. So well, I say that there should be a good condition, and it's included in that. Okay. Conditions. But there is a general theory of dyadic cubes, and if the metric space has doubling property, we can have such nice partition.
Okay.
Other questions? Perhaps in that case, we'll thank you at the end.